Hello, everyone. We're going to go ahead and go over section 10.1, which is going to be on systems of linear equations in two variables. Now, what you're about to see should look fairly familiar. You most likely have gone over this at some point, probably in high school, but we're going to revisit it. All right, so as an overview of the section, first, we just want to do some recall. So first off, a linear equation in two variables is typically of the form ax plus by is equal to c. This is known as standard form. We see the x and the y terms are being added and they're equal to some other term that doesn't have an x or y. But sometimes this is also going to be in the form of y is equal mx plus b, which should sound a little bit familiar. That is our slope-intercept form there, that y is equal to mx plus b. So you're going to see linear equations written in both forms here. They express relationships between two quantities. That's really all they stand for. They're expressing the relationship between x and y. So a solution of this linear inequality is going to satisfy an equation if it makes an equation true when the values of x and y get plugged in. So a solution, which is going to be in the form of, x comma y, because you need to have a value of x and y. Both of those values, when you plug those into your equations, it's going to make whatever equation that you have statement's going to be true. It's going to say some number equals that same number. That statement's true. So that's kind of what we're looking for with our solutions. So if we have a system of equations, that's going to be a set of equations. So most likely 2, potentially 3. You're not going to see it in 3, but we're just mostly working with 2 here. So it's going to be 2 equations that involve the same variables, x and y most often. So a system of linear equations is going to be a system of equations in which each equation is linear. So our system of linear equations is just going to be 2 linear equations, both containing the same variables, most likely x and y. So if you want to find a solution of that system, those would be values for your variables that would make both of your equations in the system true. So one value for x and one value for y that would make both of those equations true. So finding the solutions would be how you would actually solve a system of equations. So that's what we're going to be doing in this section. We see systems of equations, we're going to find out how to solve them, the different methods that we can do, and the different types of questions that we can see. So we do have a picture here, our system of linear equations in 2 variables. It's going to look something like this. We're going to see this big curly brace on the left-hand side. 2 equations kind of stacked like this, one on top of another. We call the top one equation 1, bottom one equation 2. So in this case, we have 2x minus y is equal to 5, and x plus 4y is equal to 7. So those are our 2 equations in our system of linear equations. So starting off, there are 3 methods that we can use to solve for a system of linear equations. And we're going to run through all 3, and then we're going to go ahead and do a problem. So we're going to see each 3. They, once again, should look fairly familiar to you. And then we'll go ahead and do a problem using each method. So we'll go through the methods, and then we'll work them out. So first off, we have the substitution method. And it's pretty self-explanatory. You're going to be substituting something in for something else. So to solve a system using the substitution method, you start with one equation in the system and you solve for a variable. So you solve for x or y. Then you would plug that result into the other equation to solve for the other variable. And that's about it. So you're substituting in expressions for x so you can solve for y, or substituting in expressions for y to solve for x. So our substitution method has 3 steps. Number 1 is that you would solve for one of your variables. So one of your equations, you've got x and you've got y, you would solve for one of those. So you want to isolate it to one side of your equation symbol. So you solve for one variable in terms of the other. Then you're going to take that result, step 2, and you'll substitute it. So you're going to substitute that equation that you found in step 1 into the other equation to get an equation in just one variable. So that means everything is x or everything is y. Then you would solve for that one variable that you have there. Once you do that, you should be able to have a value for one of your variables, saying like, oh, x is 2, y is 5, something along those lines. Once you have that, which was the result from step 2, you would take that value and you're going to back substitute. So you're going to substitute that value that you found in step 2 back into the expression that you found as a result from step 1 to solve for the last variable. So those are the 3 steps that we would take for the substitution method. And once again, we'll see this in action once we go over the other methods. So we're kind of just brief overviewing here. Our second method is going to be the elimination method. It's also a little bit self-explanatory. You're eliminating things. That would be the goal. So to solve a system using the elimination method, we have to combine the equations using sums and differences to try to eliminate or cancel one of the variables. So the elimination method also has 3 steps. Number 1 is to adjust your coefficients. The only way to eliminate variables would basically make them completely opposite. So you need to change your coefficients so that your functions would be opposite. Or, the coefficients in front of a specific variable would have to be opposite. So you're going to multiply one or more of your equations by some number. Doesn't have to be the same for each, it can be different. You just want to multiply them each by the appropriate numbers so that the coefficient of one variable in one equation is the negative of its coefficient in the other equation. So a lot of manipulation is going on here. Once you have that, you would add those equations together. When you add them together, you would cancel out one of those variables because they had opposite coefficients. They would just equal 0. So you would add those 2 equations, you eliminate that one variable, and you're left with the other one. And then you're left with it to solve. Once you have that value, because at this point you should have some sort of value for x or y, you would then, step 3, back substitute that value. So you would take that value that you got for x or y, substitute that back into the value that you found in step 2, so that result from step 2. Back into the original equations. So in either one of your original equations, you would substitute that value and then solve for the remaining variable. So it didn't matter which one you plugged that value that you had as a result from step 2 into either one of your original equations, doesn't matter. You just pick one. Preferably whatever looked easier to you, because that's going to be a key for a lot of these methods. Whichever one seems easier is the one that you want to go for. So, all right, here we go. Here's our last method here. We have the graphical method. So the last 2 methods that we just saw, those were more algebraic. They had lots of, pen and paper type work. This is with the graphical method. You're just graphing those equations and looking for the answer. The graphical method is definitely going to be the easiest one because all you have to do is really find that intersection point or the point where the 2 lines are going to cross. But the graphical method is not going to be appropriate to use on an exam. On an exam, you would have to use the substitution or elimination method. So in the future, just make sure you know at least one of them. It doesn't matter which one you use. Pick whichever one seems easier to you, and that's the one that you're going to want to go for. Graphical method is fairly easy and definitely totally fine to use on the homework, but on the test, you will need to know one of the other ones. So, all right, graphical method. To solve a system using the graphical method, use a graphing device to solve a system of equations. So, a graphing calculator of some kind. So, you can have a graphing calculator on an exam, which is why it's helpful to, have that. All right, so the graphical method, we have step 1, graph each equation. So, you'll take your equations. The one thing, though, is that you do want to express your equation in a form that is suitable for the graphing calculator you're using. Most handheld graphing calculators will not allow standard form, which is what we see a lot with systems of equations. They don't allow those ax plus by is equal to c. They like those equations in slope-intercept form, which is y is equal to mx plus b. So you would have to rewrite both of your equations just so that it would be in the form that your calculator likes. And we'll do that with our example. Then you would graph those equations on the same screen. Since they're both linear, they're both going to be lines. Just looking at 2 lines on a graph that will most likely cross each other. And then you're looking for step 2, the intersection point. There's just one single point most of the time you'll see we're going to go over those kind of unique situations where maybe there might be more than one after our next example. But typically you're just looking for one. The solutions will be the x and y coordinates of the point of that intersection. So fairly easy compared to the kind of algebraic ones. Remember, you have to know one of those algebraic ones for the exam. So all right, let's go ahead and do an example. We have example 1 here. We want to find the solutions to the system using the substitution method, the elimination method, and the graphical method. So we're going to do all three when we go ahead and solve for this example. Our system of linear equations is going to be 3x plus 2y is equal to 14, and x minus y is equal to 3. So all right, let's go ahead and head over onto our notes to work this problem out. All right, so here's our problem again. We've got that 3x plus 2y is equal to 14, and x minus y is equal to 3. We've labeled that top equation equation 1, and the bottom equation equation 2. So in this case, we'll be able to tell, which one we're talking about it. But all right, so since we have both of these equations here, we're going to go through each method. First method's going to be the substitution method. So we're going to label this right here, substitution method. And then second, we're going to go ahead and do the elimination method. To do our graphical method, we'll go ahead and go to Desmos. So we'll go back to our web browser. But so these are the two methods that we're going to go ahead and work out first. The first one is the substitution method. And so with the substitution method, the first step that we said we wanted to do was that we wanted to pick one of our equations and solve for one of its variables. So whenever it comes to picking this equation or solving a variable, easiest is best. So whatever looks easiest to you is what you want to go for. And whatever looks easiest to you may not be what looks easiest to somebody else. So it doesn't matter what way you go about this. If you get the right answer, it doesn't really matter exactly how you got there. Even if we pick different ways of writing these or different variables to solve for, we should always end up at the right answer as long as we're doing our problem correctly. But there's usually going to be one way that takes less steps, or maybe it's a bit less messy. So if you're looking at these two equations and you're trying to figure out which one looks easier, equation 2 is probably going to look a little easier. There's no numbers in front of x or y, so that's the one that we're probably going to lean towards. Then once you pick your equation, you want to pick the actual variable you're going to solve for. Whether or not you pick x or y to solve for first, they're both excellent choices. But picking x will make it just slightly easier. By choosing x, we won't have any pesky negatives around or anything like that. We can add y to both sides and we're basically done. So that's what we're going to do. We're going to go ahead, we're going to pick equation 2, and we're going to pick x to solve for. So we're solving for x in equation 2. So we've got x minus y is equal to 3. If we're going to solve for x, we want to get rid of the y. One way we can get rid of the y is to add y to both sides. If we do that, we end up with x is equal to 3 plus y. So added y to both sides, canceled out on the left-hand side, and added y to 3 on the right-hand side. So now we see we have x is equal to 3 plus y. Let's lower that a little bit. So that's kind of one of our answers that we're going to be using a little bit. Step 2, now that we have this value of x, is that we're going to take the expression for x and we're going to plug it into the opposite equation. So since we used equation 2 to solve for x, we need to take x's expression and plug it into equation 1. So we're going to plug in 3 plus y for x in equation 1. So instead of writing x, we'll plug in 3 plus y. So using equation 1, we'll have 3. Normally we write x, but we're replacing it with 3 plus y. So we have 3 times 3 plus y. And then plus 2y is equal to 14. So now we see our equation here only has y. So we can just solve for y. We need to do all the normal steps to solve for it, but there's no 2 variables that we just have 1. So we can go ahead and solve for y. Let's give ourselves a little bit more room here. We're going to distribute this 3 inside, and actually just use different color. We're going to distribute the 3. So we'll get 3 times 3, which is 9, plus 3 times y, which is 3y. We still have that plus 2y, and this is still equal to 14. We've got a little arrow there saying, here's our next step. That's why I write that little arrow. It is not a sideways smiley face, although sometimes it will look like it. So all right, we have 9 plus 3y plus 2y is equal to 14. We can go ahead, add the 3y and the 2y. This will give us 9 plus 5y is equal to 14. So remember, we're solving for y. We want y by itself. The next value we can go ahead and kind of simplify down is subtracting 9 from both sides. So we can write that out here if we like, or you don't have to. But if we subtract 9 from both sides, this will leave us with 5y is equal to 5. Now, we're solving for y. We just need to get rid of the 5 in front of the y. Well, to do that by dividing both sides by y. And this leaves us with y is equal to 1. So, y being equal to 1, we now know what y is equal to. We want to know what's x equal to. So for step 3, we're going to take this value that we found for y, and we're going to go ahead and we're going to plug it in to this equation here. Let's make that look a little bit more like an arrow. That's close enough. All right. We're going to take our value of y. We're plugging it in for that expression for x. So for our step here, we are going to plug in 1 for y into x is equal to 3 plus y. And we'll do that to solve for x. So we had x was equal to 3 plus y, but y we said was 1. So x is equal to 3 plus 1, which I'm sure you can all figure out. X is equal to 4. All right, so now that we have that x is equal to 4 here, we know what x is equal to, and we know what y is equal to. Our final way of writing this has to be in the form of an ordered pair, which means it has to look like x comma y within parentheses. So our final answer will be x comma y in parentheses. We said that x was 4. So we have 4 comma y, which was 1. So this would be our final answer here, 4 comma 1. When we write our answer in, when we do the homework in WebAssign, that's the form it's going to want, 4 comma 1. It will probably already have parentheses and a comma. You just need to fill in the x and y values. But that is the form it wants the answer in. Knowing that x is 4 and y is 1 is great, but you need to be able to put it in the form for the question to be marked correct. So all right, that was the substitution method. Now we can go ahead and do the elimination method. With the elimination method, we said that our first step is that we want to adjust coefficients. We want the coefficients of one of our variables, so both equations, one variable. We want in each equation there, we want the coefficient, the number in front of the variable, to be opposite, meaning 3 and -3, 2, -2, 5, -5. That's what we mean when we say opposites. Same number, but it's negative. So in our case, looking at our equations here, we have 3x plus 2y is equal to 14, and x minus y is equal to 3. The coefficient of x in equation 1 is 3. The coefficient of x in equation 2 is 1. The coefficient of y in equation 1 is 2. And the coefficient of y in equation 2 is -1, because it's a minus. So we've got quite a few different coefficients here, but it's going to be a lot easier to make a number like 1 into, say, 2, or -2, or -3. It's going to be a lot easier that way. So if we want to adjust our coefficients so that the coefficients of one variable are opposites, our best option here is trying to manipulate equation 2 to become an opposite of equation 1. So that's where we're starting. We are changing equation 2 to try and match and become opposites of one of the variables in equation 1. And whichever one you decide to go with is going to be the right answer. Whether it's x or y, they're about the same as far as difficulty level goes. So whichever one stands out to you first is the one to go with. In our case, if we multiply each one of those values in equation 2 by 2, then we'll have opposite coefficients for y. So that one might be the easiest, no dealing with any negatives or anything like that. So that's what we're going to start with. Although you could definitely multiply everything in equation 2 by a -3 as well, it would work out just the same. You'd still get to the right answer. But all right, so what we're going to do is we're going to multiply equation 2 by 2. If we do that, we can take equation 2, which we said was x minus y was equal to 3, and we're multiplying everything by 2. This will turn this equation into 2x minus 2y is equal to 6. We're going to call this equation 2a. That's what we're going to call this equation here. So now that we've adjusted that first coefficient there, we're going to go ahead and put them back in the system. But when we put them back in our system, we're going to take equation 1 and equation 2a instead. So our new system looks like 3x plus 2y is equal to 14, and 2x minus 2y is equal to 6. This is equation 1 and equation 2a. So we replaced equation 2 with equation 2a. So we can move on to step 2. You can include this new system in step 2, because really what you're doing is you're going to be adding these two equations together. So you're going to add down. You're adding those columns. So if we go ahead and we add the first column, 3x plus 2x, we're really just adding the coefficients. 3 plus 2 is 5. So we're going to end up with 5x. Then we add the next column, positive 2y plus negative 2y. This was why we wanted those numbers to be opposite, because this cancels out y entirely. Don't even have to deal with it anymore, which is the goal here. That is the goal. That's why it's called the elimination method. You're eliminating one of the variables, so you don't even have to deal with it anymore. Now that those got canceled out, we can add that last column. 14 plus 6 is going to be 20. So we've got 5x is equal to 20. We can divide each side by 5 and solve for x, which gives us x is equal to 4. So that is one value of our variables. Now we do know that x is equal to 4 because we did it in the substitution method already. But hey, there we go. That means that we verified it. All right, so we know that x is equal to 4. Your last step is always back substituting, which means that you're going to take this value of x is equal to 4 and you're going to plug it into one of the originals, equation 1 or equation 2. You could plug it into equation 2a. It'll be the same thing. But going with an original is always kind of the best. And once again, you always want to go with whatever looks easier. let's go ahead and use equation 2. So when we go ahead and do this, let's use equation 1 instead. Since we used equation 2 already, it's kind of better to get a little bit of variation going in. So we will use equation 1, actually, not equation 2 instead. Sorry for that misspoken. But all right, so we're going to plug in 4 for x into equation 2. Equation 1, I said equation 1 anyway. My bad. So equation 1, there we go. Plugging in x equals 4 for equation 1. It is kind of helpful to use the opposite one that you manipulated, just in the sense that since you manipulated one of them already, you do kind of reuse it a lot of times, and it can lead to mistakes. So it's always kind of better to try to use the opposite. If you manipulated both, then it really doesn't matter. You can use either one. But all right, let's just go ahead and use equation 1 just to make it as clear as possible. So all right, plugging in 4 for x into equation 1. We said equation 1 was 3x plus 2y is equal to 14. So if we plug this in, that means we'd have 3 times 4 plus 2y is equal to 14. So we can go ahead and simplify. 3 times 4 is going to be 12. So we have 12 plus 2y is equal to 14. We want to simplify for y. We're going to go ahead. We're going to subtract 12 from both sides. Then we'll end up with 2y is equal to 2. We're simplifying for y. We can divide each side by 2. And we get y is equal to 1, which is the same answer that we got for the substitution method. So there we go, verifying that that is definitely going to be the correct answer. And remember, your final answer needs to be in the form of x comma y. So we know x is 4, y is 1, which means our final answer would also be written as 4 comma 1. That's a final answer, which is why it's in yellow. I'll most often highlight correct answers in yellow as opposed to any other colors. So, all right. We worked out this problem using the substitution and the elimination method. These were the 2 algebraic methods. This is going to be the one that you will see on the exam. So we're going to go ahead and we're going to do the graphical method. But if you're thinking to yourself, I don't really know which one I will want to use. Typically, the one you want to use is the one that you're more practiced at. So if you're more practiced at one, that's going to be the one that you want to use. But as a rule of thumb, how it normally works is that the substitution method is very methodical. The steps that you take are always going to be the same, even if it gets messy. So the substitution method has a tendency to get messy, but it is always the same steps. So if you're really into, having those same steps, don't really care if it gets messy as much, substitution method's going to be the one that's probably for you. The elimination method typically doesn't end up nearly as messy, but it does take more of creativity. There's a lot more flexibility with the elimination method and knowing how it works. So it's going to be a lot less messy, but knowing how it works is very, very important, and it's not quite as clear cut. So it's really going to be up to you. The more practice you get, you'll end up, figuring out which one that you like more. Personally, I choose the elimination method, but I've used it a million times. So that's why I typically like it more. But when I started out, I preferred the substitution method because it was always the same steps. So it's really up to you on which one that you'll end up liking better, but that kind of is the rule of thumb for deciding which one you want to go with for, the rest of the time. So, all right, let's go ahead and head on over to Desmos to go ahead and do our problem here for number 1. Before we go ahead and plug these equations into Desmos, we want to rewrite them. Like we mentioned earlier, handheld calculators really prefer your equations when you graph them to be in slope-intercept form, which is y is equal to mx plus b, which is not how these equations look. These equations are given to you in standard form, which is ax plus by is equal to c. So if you want them in that slope-intercept form, you're going to have to rewrite both of your equations so that they're in slope-intercept form, so you'd be able to actually put them in your calculator. So we're going to go ahead and do that real quick before we actually go over to Desmos to show what they're going to look like. So starting with equation 1, which we said this was equation 1, and this was equation 2. So starting with equation 1, we've got 3x plus 2y is equal to 14. And to get our equation in slope-intercept form, we need to solve for y. So we're going to go ahead and we're going to start off by subtracting 3x from both sides. So we'll subtract 3x. That first one looks a little funny, but that's a 3. There we go. So when we go ahead and write this value out, I lost that color there. There we go. When we write this out, our 3x's were canceled. We get 2y is equal to, and we're going to write the x first because we want it in y is equal to mx plus b. So even though we subtracted that 3x, we're going to write negative 3x plus 14 first. So now we have that number in front of the x, we have the m, and we have the b. Now we got to get rid of the number in front of y. So we're going to go ahead and divide everything by 2. So every one of these values gets divided by 2. And this result is y is equal to negative 3/2 x plus 7. So there we go. That is equation 1 in slope-intercept form. So this is what we're going to use when we go to graph each equation. We're going to use this version instead of the original. We're also going to do this for equation 2. Equation 2 is going to be, a little bit easier here because we said we had x minus y was equal to 3. We just need to solve for y, start off by subtracting x. So we'll end up with negative y is equal to negative x plus 3. Now we just need to make y positive, which means that we're going to just change all of the signs. This comes about from either multiplying every value by negative 1 or dividing every value by negative 1. So whichever way that you decide to go about it. Let's say, I usually like multiplication better. Let's just say we're going to multiply each value by negative 1. That gets rid of the negative in front of y and x, and it's going to make 3 negative instead. So we've got y is equal to x minus 3. These are the two equations we're going to use in Desmos as opposed to the standard form. And especially if you're using a handheld calculator, this is really the only form that your calculator is actually going to accept it. So having it in this form is going to be very beneficial. So all right, let's head over to Desmos. All right, so here we are using Desmos. All right, if you've never seen it before, Desmos is an online graphing calculator. You just type in Desmos into the search engine, Google, whatever. It's pretty much the first link that comes up. So we have our graphing calculator here. We've graphed both of our equations, which we said are in that slope-intercept form of y is equal to mx plus b, those results that we just got when we worked it out here. And we see the equation 1 is in red, equation 2 is in blue. So we've graphed both of those lines, and we see that they are definitely intersecting at some point. Wow, the point being 4, 1. Just like how we solved for in the substitution and elimination method. We pretty much expected this to be the answer. But if you didn't use either of those methods, and you just used the graphing method, we could see it definitely ended up being quite a bit shorter. All you really had to do was rewrite those two equations and graph them, and then look for the point where they cross each other. So that's really the main part of the graphing method. It is significantly easier. There's no denying that, but can't use it on an exam. It's the only thing to keep in mind. So all right, let's head back on over to our lecture. All right, we just finished up example 1 here. Moving on, We see the number of solutions of a linear system in two variables. So what we just saw was one solution. There was one value of x and one value of y. The lines crossed in exactly one place. But that's not always true. So since your graph of a linear system is just a pair of lines, they can intersect once, which is what we saw. They can be parallel, meaning that they will never cross, or they coincide. Basically, they're laying on top of each other. They're the exact same line. So they're essentially intersecting everywhere because they're the same line. So we have our number of solutions of a linear system in two variables. So for any system of linear equations, only one is true. You either have exactly one solution, which is what we just saw like 3 times over. One value of x, one value for y, and the two lines will actually just cross in one place. So that's like our graph A here that we see. So the lines intersect at a single point. The system has one solution. Then another option is that your system has no solution. This is called an inconsistent system. You might see those words on your homework, but it means that it has no solution. The lines are parallel. That means that they're going to continue on forever in the same directions and they'll never cross each other. So that's what we see here in graph B. Lines are parallel, they will never intersect. That means the system does not have a solution. Just doesn't have one at all. Then option 3 here is that the system will have infinitely many solutions. This is also called a dependent system. So if you see that, again, that's what that means. It has infinitely many. And that's because it's the exact same line. If it's the exact same line, they're lying on top of each other, just one on top of the other. They coincide. They are the same line. The solution will have infinitely many solutions. So if you see another way that they kind of, show this, is that in graphs A and B, the two lines are red and blue. In graph C, it's purple because they're the same line. They were joined up. So blue, red, purple. All right, so that is the rundown of the types of solutions in a linear system that you can see. Most often you'll just see that it has one solution, but every once in a while you'll see that they have no solution or that it has infinitely many solutions as well. So we're going to go ahead and we're going to do an example and kind of show how this happens. Obviously, the easiest way to see if this is true is to graph those equations. But like we said, graphing the equations is probably not going to be a viable option for you on the exam. So if it's not going to be really an option for you on the exam, it's very helpful to check your answer, but you'll also need to kind of identify graphically what's going on. Or not graphically, algebraically. So we're going to do example 2. We're going to determine if the systems have infinitely many solutions or no solution. If it has infinitely many, we're going to write the general solution in terms of x. So if it has no solution, the answer is just no solution. If it has infinitely many solutions, we will have to write this general solution in terms of x, which we will get there when we do the problem. All right. We're going to have 2 separate problems here. So part A, part B. In part A, we're going to have 8x minus 2y is equal to 5 and negative 12x plus 3y is equal to 7. So we're going to use our methods, whichever one that we like. By no means do we have to use all 3. No more of that. We showed all 3 so we can go through each method, but every time you solve one of these, you're just going to pick one that you like the best. So we're going to pick one for each of these, whichever one we like more. We're going to stick with the algebraic ones just because we've already, established that the graphing one is most likely the easiest, but not useful on an exam. So part B here, we've got 3x minus 6y is equal to 12 and 4x minus 8y is equal to 16. All right, we're going to go over to our notes so we can work these problems out together. All right, so starting with problem 2a, we have our system here, 8x minus 2y is equal to 5 and negative 12x plus 3y is equal to 7. So we want to use one of our methods to solve for this, like we already said. We're going to stick with our substitution or elimination methods. So we want to think of probably which one is going to be better. Remember, the better one is the one that you feel more comfortable with. So just because we do one method doesn't mean that you can't do the other. You can absolutely do the other, whichever you like better. Remember that. So if we're looking at this system here, we're gonna just lean towards what looks like it's going to be easiest. So if we're looking at our equation, we've got even numbers, we've got odd numbers. We see in equation 1, we've got 8, 2, 5. Equation 2, we've got negative 12, 3, 7. If we try to use a substitution method, what we're going to run into is that we will have fractions in either one that we pick. And so it's going to get messy. We said that's what we see a lot of times with substitution methods. It will get messy if you don't have numbers that aren't quite as nice with each other. So that's kind of the issue that we're running into here. If you like fractions and you want to stick with the substitution method, by all means, use it. But for a problem like this, if we want to avoid kind of that messiness, we're going to go ahead and we're going to use the elimination method instead. So that's the one we're going to pick. So we're going to use the elimination method. And remember, with the elimination method, our first step is to always manipulate our equations. We said this was equation, ooh, that looks crazy. Equation 1 and equation 2. So we want to manipulate our equations so that the coefficients of one of the variables are opposites. So looking at our problem here, we want to pick which is going to be easiest. It's always easiest. If we look at our equation, the coefficients of x are 8 and negative 12, and the coefficients of y are negative 2 and 3. Negative 2 and 3 are smaller numbers, so let's just deal with the smaller numbers. So if we want them to be opposites, meaning the same number, except one is positive and one is negative, we want to find the least common multiple. The least common multiple is the smallest number that each one of our coefficients can multiply into. So in our case, our least common multiple is going to be 6. 2 times 3 is 6, and 3 times 2 is 6. So that's the number we're aiming for. We're going to turn both of these coefficients into a negative and positive 6. Equation 1, the coefficient of y is already negative, so we don't really have to deal with that. So what we're going to do here is that we're going to multiply equation 1 by 3 and equation 2 by 2. That's what we're doing here. So if we take equation 1, which was 8x minus 2y is equal to 5, we're going to multiply that by 3. And this is going to result in 24x minus 6y is equal to 15. We're calling this equation 1a. So we're going to use the a equations instead from now on. Then we want to multiply equation 2 by 2. So equation 2 was negative 12x plus 3y is equal to 7. And we're multiplying all of these terms by 2. So when we go ahead and we work this out, we're going to get negative 24x plus 6y is equal to 2 times 7 is 14. This will be equation 2a. So the new system that we're working with here, this is step 2 now, our new system will be 24x minus 6y is equal to 15, and negative 24x plus 6y is equal to 14. So we're using equation 1a and equation 2a now. And just like last time, we're adding these together. So we're going to add these two equations, and we're adding the columns. So we're going to add 24x plus negative 24x. Ooh, that's 0. Those cancel each other out. We meant to cancel out y, and if we look, We do, because we have negative 6y plus 6y. That cancels it out. So really all we have left on the left side of our equation is just 0, because both of the terms canceled out. So we have 0. And then if we add the last column there, 15 plus 14, that's 29. So if we look at this, look at our result here. 0 equals 29. Now, I don't know about you, but in no world is that true. 0 is not 29. Having 29 puppies is not the same as having 0 puppies. One makes you happy, and one probably a little sadder. So 0 is not equal to 29. This statement is just not true. And so since this is not true, that automatically means there is no solution. You will have no solution when your final statement is just blatantly incorrect. 0 equals 29. 2 is equal to 3. Anything like that. Those are just not true. Those statements are not true. They never will be true, which means that there is absolutely no solution. There's no value of x and no value of y that would ever solve both of those equations. So that's when you get no solution, when your final statement is just not true. And there's no need to do like a step 3 or anything. Once you figure that out, hey, answer's no solution, you're done. So that's what it would look like algebraically to find out that a solution or a system has no solution. If you graphed it, you would see that those lines are parallel. They will run next to each other like this and they'll never cross. All right. So that was part A for question 2. Now we're going to go ahead and do part B. For our system for part B, we have 3x minus 6y is equal to 12, and 4x minus 8y is equal to 16. Now, looking at this, we can see our numbers, the kind of numbers that we're dealing with in equation 1 is going to be 3, 6, and 12. And the numbers we're working with in equation 2 are 4, 8, and 6. All of these numbers are going to play really well with each other because we see that 3 is a factor of 6 and 6 is a factor of 12, which is also a factor of 3. Same thing, 4 is a factor of 8 is a factor of 16 as well as 4. So all of these numbers are very related. So we can pretty much figure if we're going to use the substitution method, these are probably going to solve pretty well. So we're going to use the substitution method. This will be equation 1. This will be equation 2. So using the substitution method, we said that we wanted to solve one of our equations for one of our variables. Now, solving which equation 1 versus equation 2, really not much of a difference. Whichever one you like more. Equation 1 has smaller numbers, so maybe that's the one to go with. We'll do that. So our first step here is that we're going to solve equation 1 for, and then we have to pick a variable, x or y. Well, x has the smaller coefficient, and 3 is a factor of 6, meaning that if we solve for x, we won't have any fractions. If we solve for y, we would have fractions. It wouldn't be too bad, but if you want to avoid fractions altogether, we would want to pick x. So we're going to solve equation 1 for x. So if we do this, we'll take 3x minus 6y is equal to 12. And we're going to solve for x, so we can go ahead, we're going to add 6y to both sides. This gives us 3x is equal to 12 plus 6y. And we're solving for x, so we want to get rid of the 3, its coefficient. So we'll divide each value by 3. And we get that x is equal to 4 plus 2y. All right, looks good so far. We have our expression for x now. Remember, we want to plug in this value of x into the opposite equation. So we're going to plug 4 plus 2y. We're going to plug that in for x in equation 2. So that's what we're going to write here. We're going to plug in 4 plus 2y for x in equation 2. Equation 2 was 4x minus 8y is equal to 16. So we'll have 4 times x, which is now 4 plus 2y. And then minus, not plus. Minus 8y is equal to 16. Now we just want to simplify. We can distribute our 4 into our parentheses here. 4 times 4 is 16. 4 times 2y is 8y. Then we have minus 8y is equal to 16. And we see an issue here. 8y minus 8y. Well, something minus itself is 0. So both of these terms cancel out. And really all we're left with was the 16 is equal to 16. A very similar thing just happened as it did in part A. But the thing in part A was that the statement wasn't true. 0 equal 29, 0 is not equal to 29. But in the case for part B, although a very similar thing happened, our end result is true. 16 is equal to 16. But what that tells us is that it really doesn't matter what x or y are. Any value of x and any value of y that's a solution for one is a solution for both for any values of x or y. So if 16 is equal to 16, that means that it's always true. Doesn't matter what x and y are. So in this case, our answer would be that we had infinitely many solutions. So, to tell the difference between a statement that has no solution and a statement that has infinitely many solutions working algebraically would be that your final statement, if it's not true, is no solution. If it is true, it's infinitely many solutions. Because it doesn't matter what x and y are, they're always going to be, those lines are always lying on top of each other. Or if they're not true, it doesn't matter what x and y are, they will never touch. So those are the two differences for those two different types of solution kind of values you can have. Now, there was one thing on that slide for our example. We said that if it was infinitely many solutions, we wanted to write our answer with a general solution. So that was part of that problem. And now we have one of them is infinitely many solutions. So we need to figure out what that means and what that is. A general solution to a system of linear equations, which I wrote very off to the side here, so let's bring that kind of a little bit more in the center. A general solution looks like x comma y. You got an x value and a y value. That's the general solution. But if we want it in terms of x, which is what our problem said, we want our general solution in terms of x, we need to replace y with an expression of x, which is going to be your slope-intercept form. Y is equal to mx plus b. That is the idea. So your general solution in terms of x, so we'll write that out here. We'll say general solution in terms of x is going to have to be x comma, mx plus b, because that is what y is equal to. So this is your general solution in terms of x. So you will be replacing that value of y with the mx plus b expression, which we said we can solve for y is equal to mx plus b from any one of our equations, which are given to us in standard form. So basically what this means is that if you encounter this problem, which you will in your homework, what it means is that you will take, once you've identified that it's infinitely many solutions, you will take one of your original equations. Does not matter which one. You're going to take one of them. Let's go ahead. We're going to take equation 1. We're going to take 3x minus 6y is equal to 12. And we're going to rewrite that by solving for y. So we took equation 1. You could take equation 2 if you like. This was 3x minus 6y is equal to 12. And we actually already did this. Well, no, we solved for x. So we didn't actually do this. We need to solve for y. So in this case, instead of what we did before, we're going to go ahead, we're going to subtract 3x from both sides. This will give us negative 6y is equal, and we want that x term first. So we're going to have negative 3x plus 12. And we want to solve for y, so we can divide each term by a negative 6. Negative 3 divided by negative 6 is 1/2 x. 12 divided by negative 6 is negative 2. So y is equal to 1/2 x minus 2. So our general solution for this problem needs to look like x is equal to mx plus b. In this case, m is 1/2, b is negative 2. So our general solution for our problem has to look like this. Parentheses, x, comma, 1/2 x minus 2. That would be your answer for a problem like this, a problem that asks for a general solution in terms of x. If it asks for in terms of y, it would look a little different, but don't worry, you won't run into that. So it's going to ask for general solution in terms of x. This is what you would end up doing. So, all right, that wraps up our example 2. Let's go ahead and head back over to our notes. All right, we just finished up example 2. Let's move on to this last kind of subsection in section 10.1. So our last topic that we're going over is modeling with linear systems. So we just saw how solving systems of linear equations went. Now we're going to be looking at how would we recreate a system of linear equations with most likely a real-life application. So we're going to be modeling real-life events with linear systems. So we have some guidelines to kind of help us a little bit here. First is that we want to identify our variables. We want to identify the quantities our problem is asking us to find. These are usually determined by some reading of the question, very careful reading, and at the end of the problem. At the end of the problem, it's going to ask you a very specific question. So you want to make sure that the quantities and variables that you're using are going to pertain to that question. Then you would introduce notation for your variables. You call them x or y. You could pick other letters if you'd like as well. X and y are pretty typical though. So first is just identifying the variables, identifying the things that you are solving for, and then assigning them values. So that leads us to step 2. Express all your unknown quantities in terms of the variables. You'll read your problem again, express everything in terms of the variables that you defined in step 1. So if you said X and Y were something, you would then attribute whatever other information that you had to those variables. Step 3, set up a system of equations. You would take those crucial facts in the problem that give the relationships between the expressions that you found in step 2. So basically step 2, you want to try and just set up those actual equations. And then step 3 is just putting them in a system. So basically stacking them and putting a big curly brace around it. So you want to set up your systems of equations or a model, same thing, and it expresses these relationships. So you put it in your system, and step 4 would be you actually solve that system and you interpret your results. So at the end, whichever result you got, you can express that as whatever it was that you were trying to solve for. So these are the 4 kind of steps, the guidelines that you have for if you want to recreate a real life situation with systems of equations, which is what we're going to use when we do our very last example here, example 3. So example 3, we have a gas station sells regular gas for $2.20 per gallon and premium gas for $2.70 per gallon. At the end of a business day, 310 gallons of gas were sold and the receipts totaled $712. We want to know how many gallons of each type of gas had been sold. So if we're looking at this equation, what we're seeing is that we have regular gas and premium gas. They both have separate prices, and we know how much the amount was sold at the end of the day and how much that amount actually cost. Our final question is how many gallons of each type of gas has been sold. So if we're looking for types of gas, we're looking at regular and premium. So regular and premium are going to be our variables. We can say regular is X and say premium is Y. Then we have lots of things that we can now attribute to this. We know that regular gas is $2.20 per gallon. If X represents some number of gallons of regular gas, X would be a number amount of gallons. So we know that X is actually going to be regular gas. So we could say that 2.20, which is $2.20, times X would represent cost and gallons of regular gas. We can do the same thing for premium gas. Premium gas we could say is Y, and it costs us $2.70. If Y is the number of gallons, we can multiply that by $2.70 to see how much somebody was buying of premium gas. Then we say that at the end of a business day, in total, there were 310 gallons of gas, meaning that X plus Y is equal to 310. Some number of gallons of gas, which is X, of regular gas, X, and some number of premium gallons of gas, Y, is equal to 310. And we want to know how many gallons of each type of gas has been sold at the end of this day. Knowing that regular gas is X and premium gas is Y, we can go ahead and start setting up our equation. So let's go ahead and head on over to our notes. All right, so from problem 3, I rewrote just the important information here. Regular gas sells for $2.20 per gallon. Premium gas sells for $2.70 per gallon. There were 310 gallons of gas that were sold, and there was a $712 profit. So for our guidelines, we said step 1 was just identifying the variables. So for us, step 1 is going to be assigning regular gas and premium gas a variable. So let's make it easy. Stick with X and Y. We're going to say that X is gallons of regular gas. It's some number of gallons, but we don't know what it is. But X is just representing any number of gallons of regular gas. So any arbitrary number. It can be any number that we want it to be. Same thing for Y. Y is going to be gallons of premium gas. So we've assigned X to gallons of regular gas and Y to gallons of premium gas. So we've identified our variables. Step 2 is that we want to relate the other information that we were given in our problem to the variables that we have determined. So one way that we can attribute this right off the bat is that we know the price for regular and premium gas. We know that regular gas is $2.20 per gallon and premium gas is $2.70 per gallon. So if we want to attribute these values to X and Y, we know its price point, they're going to be multiplied. Because for every gallon, every single gallon of gas, the price will go up by $2.20. So we can have, say, 2.20 times X represents the cost of gallons of gas. And this is regular gas. $2.70 times Y would represent the cost of gallons of premium gas. Then we have some other information that we were given. We want to remember that there were 310 gallons of gas that was sold, and there was a $712 profit. So focusing first on that first piece of information, there were 310 gallons of gas that were sold. And we said that X was gallons of regular gas and Y was gallons of premium gas. And the combination of these equaled 310 gallons of gas in general. So if X is the gallons of regular gas and Y is the gallons of premium gas, that means that adding those together would give us a total of 310 gallons of gas. So one equation that we have here should be X plus Y is equal to 310. That's one of our equations. Now our other equation, if we kind of look at the information that we have, what we haven't used yet is that we haven't used, the cost of the gallons of regular gas and the cost of gallons of premium gas, and we haven't used the $712 profit. And this is where it's all going to come together. So this first equation that we identified was a quantity equation. It was how much of X and Y equals a certain number. So that was a quantity equation. The next equation that we're going to identify is the price. We said it was a total of $712, and the price of the gallons of regular gas plus the price of the cost, or the gallons of premium gas, all of that is going to be equal to $712 because it's the price times the number of gallons for both types of gallons. So our other equation should look like the cost of gallons of the cost, per gallons of regular gas plus the cost per gallons of premium gas will equal the amount, we actually don't have to put the dollar sign anymore, is equal to the profit. This was cost. And cost, all it really does is it describes quantity. So for this specific problem, we had quantity and then how much that quantity cost. But this happens a lot with these types of problems. The types of problems that you will run into is that you have something like an amount, a quantity of some kind, maybe, time, gallons, any number of things that can be kind of this quantity aspect. And your other equation will most likely end up being something that would describe that quantity. Cost described the number of gallons because we could attribute one with the other. Maybe energy can describe, time or something along those lines. So that's what you're looking for when you're looking for your equations. So now that we actually have the two equations, this leads us into step 3. Step 3 is just putting them in the system. So here we go. Here's our system. We've got x plus y is equal to 310. And 2.2, we're going to leave off those zeros. We don't have to include them. It doesn't really change anything about our problem, so we're just going to leave the zeros off. We're going to have 2.2x plus 2.7y is equal to 712. So we want to go ahead, we want to solve this system. You can use any method to solve the system, any method that you like. You can use substitution, elimination, graphical method, once again, whichever one you like. Since I'm doing the problem, as always, I prefer the elimination method, but the substitution method totally works here as well. Whichever one you like to use is the one that you want to use. So for step 4, for what I'm going to do is that we're going to do the elimination method. The way that we're going to do the elimination method, remember, we just want opposite coefficients. So whether you pick, coefficients of x or coefficients of y, doesn't matter. I'm going to pick the one that's slightly smaller. I'm going to pick the 2.2 instead. We can say this was equation 1 and this was equation 2. So for my first step, I'm going to multiply equation 1 by a negative 2.2. So every value is going to be multiplied by a negative 2.2 in this case. So once I do that, we'll go ahead. We'll take negative 2.2 times x plus y is equal to 310. And this gives us our new equation, negative 2.2y minus 2.2. Sorry, I said y first time. That is an x. There we go. Minus 2.2y is equal to 310 times negative 2.2, which was negative 682. So this will be equation 1a. So putting this back into our system means that we can now use equation 1a and equation 2. So equation 1a, we've got negative 2.2x minus 2.2y is equal to negative 682. And then we've got 2.2x plus 2.7y is equal to 712. So equation 1a and equation 2. We're going to go ahead and we're going to add them up. So those first values, the coefficients and x, cancel each other out because that was the point. Then we have negative 2.2y plus 2.7y. This gives us 0.5y is equal to, and negative 682 plus 712 equals 30. So we want to get rid of the 0.5y here. So we're going to go ahead, we're going to divide each side by 0.5y. Which is going to give us y is equal to 60. So we know now what y is equal to. So if we know what y is equal to, we can go ahead and pick one of our equations that we can go ahead and plug this value of y back into to solve for x. Looking at our equations, equation 1 is going to be the easiest. So let's pick equation 1. So for step 3, we want to plug in 60 for y in equation 1. Equation 1 was x plus y was equal to 310. So x plus 60 is equal to 310. We're solving for x. We'll go ahead, we'll subtract 60 from both sides. Which leaves us with x is equal to 250. So we know what y is and we know what x is. The last thing that we need to do, which is a very, very minor step here, but the last thing is relating it back to the problem. The question was, how many gallons of regular gas and how many gallons of premium gas did you sell? So in this case, our answer would be that we sold 250 gallons of regular gas and 60 gallons of premium gas. So when it comes to the final answer, that is our final answer. We sold 250 gallons of regular gas and 60 gallons of premium gas. So, all right, that would be how you would go about attempting a kind of real life application problem and turning it into a system of equations and then actually solving that system of equations. So, all right, let's go ahead and head back over to our lecture. All right, we just wrapped up example 3, which finishes out our section 10.1. So here's our summary. In section 10.1, we learned about the substitution method, we learned about the elimination method, the graphical method, the number of solutions of a linear system, and finally, modeling with linear systems. So, all right, that finishes up section 10.1, and I'll see you in the next section.